Okay, next we have some traveling problems. So traveling is basically when we're looking at sort of more the map side of things for networks. So like I said, a network can be represented as sort of like a map. So when we are basically representing these types of graphs, we can also have different types of ways in which we can navigate through that network. And these can be in the form of walks, trails, circuits, paths, and cycles. And all of these have different sort of classifications. So a walk is basically when we have a sequence of edges that link with vertices. So starting at one point and then going to another point. Walk is basically the simplest type of sort of movement, and literally everything classifies as a walk. So walk is sort of like the generalized term for a sequence of, basically a sequence going through a network. Next we have trail. So trail is a little bit more of a specified type of walk. So it's a walk where we are not repeating any of the edges. So I'll go over what all of that means in a second. But I'll first just like to explain what all of these are. Then we have circuits. So circuits are a type of trail in which we start and end at the same vertex. So we start at one point and we end back at the same point, but we're not repeating any edges. A path is a specialized type of walk where no vertices are repeated. So trail, no edges. Path, no vertices. But technically, you're not repeating any edges either. So for a path, if you're not repeating any vertices, how can you repeat an edge? So basically, you can sort of say it's a specialized type of trail where we're not repeating any vertices. But anyways, and then we have cycles. So a cycle is a type of path, essentially, where we start and end at the same vertex. And we are not repeating any edges or vertices. Okay, next we have specialized types of trails and circuits. So, first we have Eulerian trails. It's a special type of trail. And in this trail, we must visit every single edge in the network diagram exactly once. And following all the other rules of trail, which is not repeating any edges. So therefore, the only special rule here is that we must visit every edge. But for just a normal trail, there's no sort of rule that we have to visit every single edge. But for Eulerian trails, we do. And an Eulerian trail will only exist if a vertex has an even degree, except exactly two vertices which have an odd degree. So for an Eulerian trail to exist even, all the vertices need to have an even degree, except for exactly two which have an odd degree. That's the only way for an Eulerian trail to exist. Then we have Eulerian circuits. So Eulerian circuits, being very similar to an Eulerian trail, but must start and end at the same vertex. And in this case, in order for an Eulerian circuit to exist, the degree of all of the vertices in the network diagram must be even. Okay, next we have Hamiltonian paths. So Hamiltonian paths are a special type of path in which every vertex must be visited exactly once. So we need to pass through every vertex on the network diagram exactly once. So for a normal path, there was no rule on that. For a Hamiltonian path, we need to go through every single vertex. Hamiltonian cycle, similar to a path, visiting every single vertex without repeating any vertices, but we now must start and end at the same vertex. So those are all the specialized types of paths, cycles, traveling sort of situations. Here's just sort of like a summary table to summarize what they basically are. So walks, can use edges more than once, can use vertices more than once, do not have to start and end at the same vertex, and can start and end at the different vertices. So it doesn't mean a walk can't start and finish at the same vertex. It can. It doesn't have to. And so on and so forth. So a really good summary table, just having your bound reference or just at the back of your notebook somewhere. But let me just quickly go through what I mean by a walk or a trail. So basically you'll get something like this, and you'll be asked to identify a walk. So walk will literally just be DAC, that's a walk. EBC, that's a walk. EB, that's a walk. And then a trail, a walk with no repeated edges. That could be, for example, DABE. We haven't repeated any edges. A circuit, that could be something like ACB. ACB. That's a circuit. A path, walk with no vertices are repeated. DACBE. No vertices are repeated. So that's essentially what you'll be asked to do. So identify the actual sequence. Eulerian trail, Eulerian circuits, Hamiltonian paths, Hamiltonian cycles, a little bit more specialized. And remember, for an Eulerian trail to exist, only 2 of the vertices can be odd. So in this case, we have 1, 2, 3, more than 2 vertices which have an odd degree, which means that neither can an Eulerian trail nor an Eulerian circuit can exist. So they don't always have to exist. What about a Hamiltonian path? That is a little bit more trial and error. We just have to work it out and see if it works. A Hamiltonian path, yes, I think it will exist. So DACBE. And remember, there are multiple alterations to this. There's not just one clear answer. But a Hamiltonian cycle will not exist, because if we start at, for example, A, we go D and then we have to come back. Or we start at D, A, we can't come back to D without repeating any edges or vertices. So basically that is what this topic sort of really revolves around. But yeah, that's basically it for this lecture. There's not a lot in terms of content that we need to go through.